This is Chapter 4, Goal 19, and we're talking about inverse sine function. Before you can fully understand the inverse sine function, I want us to review a few facts about inverse functions themselves. In order for a function to have an inverse, that function must be a one-to-one function. Recall the horizontal line test. So if you see this horizontal line, if I lay it across y equals sine of x graph, you can see that I cross that horizontal line in multiple places. So in and of itself, the sine function is not a one-to-one function. It's only a one-to-one function if no horizontal line intersects the graph more than once. And this one clearly does. So we'll talk about in a moment, how do we handle when it does not pass the horizontal line test. The second thing we need to recall about an inverse function is if the point xy is on a graph of f, then yx is on the inverse function. So remember, inverse functions swap the domain and range from the original function. We notate inverse functions f to the negative 1 of x. Now we don't read that f to the negative 1. It's not actually a power, this is notation. Read f inverse of x. Finally, recall that the graph of the inverse is a reflection of the graph of f about the identity line. And remember, the identity line is y equals x. Okay, so sine definitely does have an inverse function, but we need to be able to handle this fact that it fails the horizontal line test. And in order to handle that, we can restrict the domain. So we must restrict the domain of y equals sine of x. How do we do that? Well, first of all, you know the domain is all reals. So I'm going to take this little window here and I'm going to slide it along this function. And I want you to watch what happens as we go through. All right, so if I start here, if I stop sliding here, I have a one-to-one function. But if I continue to slide, and if I stop between negative 2 pi and negative pi, my function is no longer one-to-one. Continuing, it's one-to-one again. Continuing, it's no longer one-to-one. Still not one-to-one. Still not. And now it's one-to-one again. And I can continue. It's not one-to-one. It's not. And now it's one-to-one again. So you'll notice that it's one-to-one every time I am on an odd multiple of pi over 2. So we will restrict the domain for y equals sine of x to negative pi over 2 to pi over 2. So the restricted domain for y equals sine of x is negative pi over 2 to pi over 2. Okay, so what is the range? Do we need to restrict the range? No, it is not necessary to restrict the range to have a one-to-one function. So our range is still negative 1 to 1. Okay, so I'd like you to highlight this section of y equals sine of x and also draw the window around it so you see the restriction. Okay, so I'd like to use this information to help us graph the inverse function. Recall that the inverse function, the domain and the range swap places. So the restricted domain of y equals sine x becomes the range of the inverse sine. The range of y equals sine x becomes the domain of the inverse sine. Okay, Well, let's use that information to sketch a graph here. So we know that the negative pi over 2 to positive pi over 2 is now our range. And negative 1 to 1 is now our domain. And then I'll take these ordered pairs from y equals sine of x. This ordered pair is negative pi over 2, negative 1, and swap it. And now we will go left 1, down pi over 2. 0, 0 stays put. And then we'll swap negative pi over 2, 1 to 1, positive pi over 2. Notice how the graph of sine between negative pi over 2 and 0 is concave up. So the inverse will be concave down. Notice between 0 and pi over 2 that sine is concave down, so the inverse will be concave up. And now we have the graph for inverse sine, or arc sine of x. Another thing that I would like to note, in y equals sine of x, recall that the x represents theta and y represents the opposite over the hypotenuse. So when you switch to the inverse, remember these will swap places. So y is now your theta, and you're taking the inverse sine of the opposite over the hypotenuse. Finally, before we start actually working with inverse sine functions, I want you to see how this graph of inverse sine of x shows up on the unit circle. So I know that my placement of negative pi over 2 and positive pi over 2 on the unit circle, negative pi over 2 is on the negative y-axis, and positive pi over 2 is on the positive y-axis. And as we move across or move up through the inverse sine, I have 0 radians. And as we continue, I would be at pi over 6 radians, pi over 4, pi over 3 radians. So I'd like to also mark those on the unit circle. And then, of course, into the fourth quadrant, negative pi over 3, negative pi over 4, and negative pi over 6. And I know for inverse sine, or for sine only, the value at pi over 2 is 1. Remember, our ordered pair there is 0, 1. The ordered pair at pi over 3 is 1/2 root 3 over 2. The ordered pair at pi over 4 is root 2 over 2, root 2 over 2. The ordered pair at pi over 6 is root 3 over 2, 1/2. At 0 is 1, 0. And then you know into the fourth quadrant, all of the y coordinates become negative. So when we are evaluating y equals inverse sine of x, or remember we already discussed that this y is your theta, theta equals the inverse sine of opposite over hypotenuse, we will be given the opposite over hypotenuse and have to identify the angle. And so we will only be working in quadrants 4 and 1. So let's take a look at these first 3 examples. Recall our inverse function, y equals the inverse sine of x can be translated as theta equals the inverse sine of opposite over hypotenuse. So we've been given opposite over hypotenuse. Root 3 over 2 is the opposite. Over 1 is our hypotenuse if we're using the unit circle. and we're asked to find theta. So if we go over to our unit circle, and I'll find root 3 over 2, and that's at pi over 3. So theta is equal to pi over 3. The second example, theta is equal to inverse sine of -1/2. So it's asking at what angle does sine equal -1/2? Because this is a negative, we know sine is negative in quadrant 4, so we will have to go to quadrant 4 to find our solution. And I know that the sine at -pi over 6 is -1/2. So theta is -pi over 6. In our third example, we're looking for where theta equals arc sine of 0, or at what angle does sine equivalent to 0. And if we look at the ordered pair at pi over 2, the sine is 1, but at 0, the sine is 0. So theta is equal to 0 radians. I'd like you to pause the screencast and try the next 2 examples. Remember, when you're given an arc sine, you're solving for the corresponding angle measure. All right, let's see how you did. On the fourth example, theta is equal to -pi over 3. If you look at -pi over 3, the ordered pair is 1/2 negative square root of 3 over 2. The sine of negative root 3 over 2 is equivalent to -pi over 3. The fifth example, theta equals arc sine of -1. On the unit circle between in our restrictions, -pi over 2 to pi over 2, sine equals -1 at -pi over 2. And finally, for the last example, we're given the inverse sine, again, of opposite over hypotenuse. So this would be opposite leg of 2 over the hypotenuse of 1. When does a hypotenuse ever equal 1 when the opposite leg is 2? Or when is the hypotenuse ever smaller than a leg? And it's not. So this would be undefined. Recall, if you look back at our inverse functions, domain and range. The domain of inverse sine is from -1 to 1. 2 is not between -1 and 1. Therefore, this function is undefined. Please make sure you memorize the restrictions for sine in order for it to have an inverse. The restricted domain for y equals sine of x is -pi over 2 to pi over 2, which means it becomes the range of inverse sine. The range of y equals sine of x is -1 to 1, which becomes the domain of inverse sine.